The paper explores the potential of large language models, LLMs, in enhancing instructional design, with a focus on scaling evidence-based expertise. It highlights both the benefits and limitations of AI-driven content generation, emphasizing the importance of human oversight for quality assurance. 2 case studies are presented, demonstrating the application of GPT-4 in creating complex assessments and active learning components. The authors also share best practices for utilizing LLMs, including template utilization, fine-tuning, and handling unexpected outputs. This research aims to bridge the gap between theoretical educational studies and practical implementation, contributing to understanding and optimizing the use of AI-driven language models in educational settings. The judicious application of AI-driven language models, such as GPT-4, in educational settings holds significant potential for creating higher-order assessments. This research explores 2 case studies, leveraging the author's experience as a learning engineer at Carnegie Mellon University, to enhance courses by incorporating active learning components for students. In the first case study, a course on e-learning design and principles aimed to apply 30 instructional principles in practice. GPT-4 generated open-ended questions, hints, and explanations aligned with these principles, providing an interactive learning experience. However, the reliability of GPT-4's output was inconsistent, particularly in complex subject areas, necessitating human supervision to validate and maintain content quality. The second case study focused on a course on statistical reasoning, employing GPT-4 to create multiple-choice questions, faded worked examples, and self-explanation prompts tailored to the course's learning objectives. While GPT-4 demonstrated potential in generating educational content, it required careful oversight due to inconsistencies in its output, especially when dealing with nuanced statistical concepts. The findings underscore the importance of balancing the use of AI-driven language models with human expertise in educational settings. While GPT-4 can automate assessment creation and provide tailored content, it is crucial to ensure that the generated material aligns with the intended learning objectives and maintains accuracy and quality. This necessitates ongoing collaboration between educators and AI systems to leverage the strengths of both parties effectively. By understanding the potential benefits and challenges associated with using AI-driven language models, educators can harness their power to enhance learning experiences while mitigating potential risks. A balanced approach combining the capabilities of AI-driven language models with the expertise of educators is essential for creating high-quality educational content. The development of the Learning Analytics and Educational Data Science course for Fall 2023 focuses on implementing predictive models using Python. The learning objective is to deliver nuanced and evidence-based guidance regarding the effectiveness of selected instructional principles, considering boundary conditions in a given context. The course employs a scenario-based predict, observe, explain (PO) method for each instructional principle, with an emphasis on the spatial contiguity principle. For instance, creating a single case study for the worked example principle required several days and multiple iterations. To scale this process, one-shot prompting was utilized. A sample prompt for the spatial contiguity principle involves identifying boundary conditions, creating assessments in the form of predict, explain, observe, explain scenarios, and generating feedback for multiple-choice questions and short answers. The figure illustrates an example of a predict, explain, observe, explain activity generated by GPT-4, focusing on the spatial contiguity principle for one-sided reference. A subject matter expert has added annotations to evaluate the quality of the content, highlighting both the strengths and limitations of using GPT-4 generated content in this context. To craft effective prompts, the authors iteratively designed a series of prompts through trial and error. The first prompt requests 2 examples of hands-on exercises that cover the learning objective. Implement a predictive model using Python, in a module called classifiers. The second prompt asks for a worked example in Python, including the corresponding code for one of the hands-on exercises provided in the previous prompt output. The third set of prompts, averaging around 3 to 5, aims to debug any errors that appear when trying to run the code provided in the prompt 2 output in Google Colab. This is based on the development of 3 exercises using different datasets for the learning objective above. Finally, for each step in Jupyter Notebook, The authors want to create practice activities like those provided in the appendix. These activities are designed to engage learners and enhance their understanding of the predictive model implementation process. In a Jupyter notebook, Figure 2 illustrates a sequence of practice activities designed with GPT-4 assistance to help students learn identifying at-risk students using predictive models in Python. The provided code snippet serves as a guide for students to verify their understanding by checking for correct usage without revealing the answer. Initially, a one-shot prompting strategy was employed, similar to the previous case study. However, it was found that few-shot prompting yielded better results. Notably, GPT-4 did not generalize the Altair library in the output Python code, as shown in Figure 2, despite all examples in the appendix consisting of it. A few instructions were edited, focusing on steps not suitable for this format, such as reading datasets or training classifiers, which were covered in the student's prior knowledge. The authors present best practices for instructional design when utilizing large language models, such as GPT-4, in educational content creation. They recommend utilizing templates for instructional design tasks to improve the quality of generated output by enhancing structure and consistency. Fine-tuning for novel instructional problems is crucial, with adjustments in the temperature value controlling the focus on specific knowledge components or facilitating broader transfer. Handling unexpected output is essential, involving iteration of the prompt to identify patterns and define explicit rules. Implementing LLM chains for multi-step instructional tasks is also recommended, breaking tasks into smaller subtasks to improve output quality. Figure 3 showcases ChatGPT's capability to generate learning objectives for an educational game design, as well as critique one of them. This exemplifies the model's self-awareness and ability to evaluate its own output. This case study underscores the significance of verifiable learning objectives in game-based education, which can enhance the overall learning experience. ChatGPT's self-evaluation process involves assessing the generated learning objectives against a set of predefined criteria, ensuring they are specific, measurable, achievable, relevant, and time-bound, SMART. This critique process enables the model to refine its output, ultimately producing high-quality learning objectives that align with the game's educational goals. The study highlights the potential of integrating AI-driven tools, like ChatGPT, into educational game design to facilitate the development of effective learning objectives. By automating this process, educators can focus on higher-level tasks, such as game development and pedagogical design. This synergy between AI and human expertise can lead to more engaging and effective educational experiences. The case study also underscores the importance of incorporating self-evaluation mechanisms into AI-driven tools, enabling them to reflect on their own performance and iteratively improve their output. This self-awareness is crucial for developing trustworthy AI systems that can operate effectively in complex, dynamic environments. The proposed recommendation system aims to close the loop in educational technology by leveraging a customized version of GPT-4. This advanced system will extract information from educational studies, encode data into a database, and generate assessment applications. The system's primary objective is to tailor instructional design strategies to user-specific needs, including target learners, learning objectives, and subject area. By doing so, the system seeks to democratize instructional design expertise, streamline the design process, and ultimately enhance educational outcomes. This ambitious project builds upon the significant contributions of Professor Ken Codinger, John Stamper, and students from Human Learning and how to optimize it, as outlined in the Model Human Learner document. The study compares the effectiveness of worked examples versus practice problems in teaching programmable logic controller (PLC) programming to novices with no prior exposure to relay circuits or PLC programming. Two groups were examined. Group A, which alternated between 12 worked examples and 12 practice problems, and Group B, which received 24 practice problems. The results indicate that the worked examples condition was equivalent to the problem-solving condition, with the addition of examples of relay circuits and their corresponding programming steps. Participants were asked to mentally follow the programming steps to ensure correctness. This research highlights the efficacy of using worked examples in PLC programming, particularly for beginners. In the realm of instructional design, a crucial question arises. Do worked examples or problem-solving tasks better facilitate learning for novice students? To investigate this, researchers compared the efficacy of these two approaches in a controlled study. In the worked examples condition, participants studied 12 examples and then attempted 12 problems, whereas in the problem-solving condition, they tackled 24 problems directly. The results unequivocally demonstrate that worked examples yield greater instructional efficiency, as manifested in higher post-test scores achieved in less instructional time. This outcome implies that worked examples are a more effective instructional strategy for novice learners. Furthermore, the study explores the application of data visualization problems in few-shot prompting, a technique where learners are presented with a limited number of examples to facilitate rapid adaptation. A case study is presented, showcasing the potential of this innovative approach in educational settings. In the realm of cognitive load management, worked examples have been a subject of interest in instructional design. This study examines the effectiveness of worked examples for inexperienced learners, investigating the worked example effect and its implications on learning outcomes. The first experiment revealed a significant worked example effect, where learners who received worked examples outperformed those who did not. This outcome suggests that worked examples can mitigate the cognitive load associated with problem solving, facilitating learning for novice learners. However, as learners gained experience, the effect disappeared, indicating that more experienced learners benefited from the practice opportunity without the cognitive overhead of seeing a worked example. The results imply that worked examples are most beneficial for learners with limited prior knowledge, as they provide a cognitive scaffold for problem solving. In contrast, more experienced learners may not require this support, and the worked example may even hinder their learning by introducing unnecessary cognitive load. This study's findings have significant implications for instructional design, highlighting the importance of adapting instructional strategies to learners' levels of expertise. By providing worked examples for novice learners and gradually phasing them out as learners gain experience, instructors can optimize learning outcomes and minimize cognitive load. The study's methodology employed a mixed design experiment, combining both between subjects and within subjects factors. The results were analyzed using a 2x2 ANOVA, revealing a significant interaction between the worked example and experience factors. The findings are presented in detail in the accompanying tables and figures, providing a comprehensive understanding of the worked example effect and its applications in instructional design. Interactive and dynamic visualizations can be generated using Altair, a Python library for statistical visualization, as demonstrated in Figure 4. This library enables the creation of scatter plots that showcase the relationship between two variables in a dataset, such as x and y, which represent different attributes of the data points. The plot includes a tooltip that displays additional information about each data point when hovered over, enhancing the interactive nature of the visualization. Altair's API allows for the specification of encoding channels like x, y, color, and size, which can be mapped to different columns in the dataset. This flexibility enables users to encode various aspects of their data into the visualization, providing insights into patterns and relationships within the dataset. Interactive tools, such as zooming, panning, and selecting, facilitate deeper exploration of the data, revealing trends, outliers, and correlations that may not be immediately apparent from static visualizations. Beyond scatter plots, Altair supports a range of visualization types, including bar charts, histograms, and line plots. The library's emphasis on interactivity and customization makes it an ideal choice for researchers and practitioners seeking to present complex data insights effectively. By leveraging Altair's capabilities, researchers can efficiently communicate their findings and facilitate further analysis and discussion among stakeholders, ultimately enabling more effective data-driven decision-making. Figure 5 illustrates the incorporation of tooltips in Altair, a feature that significantly enhances the interactive capabilities of visualizations. By leveraging Altair's tooltip function, researchers can create interactive plots that provide immediate access to underlying data values when users hover over specific elements. This functionality is crucial for facilitating detailed exploration of the data and improving user experience. The example demonstrates the versatility of Altair as a visualization tool, showcasing its ability to generate complex and interactive plots with ease. The tooltip feature is particularly useful in situations where displaying all data points directly on the plot might lead to clutter, allowing users to focus on specific areas of interest without being overwhelmed by information. Moreover, the integration of tooltips in Altair visualizations can be seen as a step towards creating more immersive and engaging data exploration experiences. It encourages users to interact with the data in a more dynamic manner, which can lead to new insights and discoveries that might not be immediately apparent from static visualizations. By incorporating tooltips, researchers can create interactive visualizations that offer a more detailed and nuanced understanding of the data. This feature not only improves the readability of complex plots but also fosters deeper engagement with the data, making it an invaluable tool for researchers and practitioners working in various fields of data science.